Howdy, folks. How's everyone doing today? Y'all got any big weekend plans? Isn't Dawn supposed to be this weekend? How's that even working this year, by the way? No clues. Everyone can hear me, right? Am I? Oh, okay. Okay, there we go. Good. Dancing on Zoom. Well, that seems just not quite as exciting. Alrighty, let's get started. Okay. So today we're going to talk, finally, going to do some, we've done a bit of calculus already, I guess, but going to get into calculus of functions of several variables. And we're going to start by talking about partial derivatives. Okay, so let's remind ourselves what a derivative is for a function of one variable. So if we have a function of one variable, f of x, then the derivative of f at a, so f prime of a, is the rate of change, don't care about antivirus, of f whenever x is equal to a. So in other words, the rate of change of f at a is, if you're at a and you change your x by a little bit, so your x equals a, you change x by a little bit, how much is your function changing? So it tells us how f changes if we change x by a little bit, say from a to like a plus h for some small h. So if we increase or decrease a by a tiny bit, how is f changing? Oops. So f prime of a, the limit definition is the limit as h goes to 0 of, so the difference in f when we change x from a to a plus h, so we move x by a tiny bit, so that's the change in f over how much did we change x by h. And if you want to get an approximate thing, you can just take away the limit bit. But if this is, say, our a right here, and we go to a plus h, so that's f of a, that's f of a plus h. That's how much x has changed, that's how much f has changed. And so it's the slope of the tangent line in that case. Change in y over change in x. But basically, it tells us how does the function change. It gives us an idea of how the function changes when you change x by a small amount. So if we have a function of two variables, now we have two things that we can change about the function. So we can change x by a little bit, or we can change y by a little bit, or both. But we can look at how f changes. When we change x and y by a little bit separately. So for instance, if we leave y fixed, but we change x by a little bit, how does our function change? Or if we leave x fixed and we change y by a little bit, how does our function change? And the two could be very, very different things. So that's the idea of the partial derivative. So here's the partial derivative. It's basically the same thing as the derivative, but we're only changing. Now we have two variables and we leave one of them fixed. Okay, so the partial derivative of f with respect to x at ab, which we can also write as so df dx at ab, but notice I'm using a rounded, a fancy d, if you will. And we'll see that we use these rounded, these fancy d's for partial derivatives and the normal d's for regular derivatives. So partial derivatives implies you have more than one variable, but we'll cover that more when we have to deal with it later. Okay, so the partial derivative of f with respect to x at ab is the limit as h goes to 0. So what we're doing is we're fixing y, and we change x by a little bit by h. So f of a plus h, b minus f of ab. So we're at ab. We change x from a to a plus h, and we leave y fixed at b, divided by the change in x, which is h. And we take the limit as h goes to 0.
Why is it only a plus h? Why not b plus h in this?
So because b is the y coordinate, and what we're doing is we're leaving y fixed in this case. So we're fixing y at b, and we're just changing the x value by a little bit.
Oh, so for the example that you said above, we're looking for the change in x only here.
Exactly. So we want to leave y fixed, and we want to see what happens when we change x by a little bit to our function. So that's why we do that. So that's the partial with respect to x, f sub x. The partial with respect to y is exactly the same thing, except, well, the opposite. We leave x fixed and we change y by a little bit. So that's f sub y, or df dy with the fancy d's at ab. So that's the limit. We'll call it k because the book calls it k. We'll see why later when we get to directional derivatives, but it doesn't really matter. So f of a, now we change y by a little bit. So f of a, b plus k minus f of a, b. So we've left f at a, or x at a. We're changing y from b to b plus k, and then we're looking at how the function is changing. That's the numerator. Divided by how y is changing by k. And then we take the limit as k goes to 0. Okay, so these are right. So these are the limit definitions, but of course this is not how we actually calculate things in 140 and 141 using the limit definition of the derivative, and that's not how we're going to do it here. So it turns out it's actually, you already know how to calculate these derivatives using all the rules you've already learned. The way we're actually going to calculate this so to calculate the partial with respect to x, so we're going to look at our function, and we're going to treat y as a constant. So you look at your function, you're no longer thinking about a function of two variables. You're thinking it as a function of x now, and y is just some constant. Then you're going to differentiate, as usual, using all the rules you know. With respect to x. All right, so now you're just treating it as a function of x, y is just some constant now, and you differentiate using the usual rules. That's how we take the partial with respect to x. Treat y as a constant, differentiate as usual with respect to x. And the same thing to calculate f sub y. Now we treat x as a constant. And then we differentiate as usual. Now with respect to y. So for example, suppose our function is, say, x cubed natural log y. It's a function of two variables. So if we want to calculate the partial with respect to x, we now treat y as a constant. So in our function, natural log y, we're thinking in our head that is now a constant. So it's x cubed times some constant. And then I'm just going to differentiate with respect to x. So what happens to x cubed natural log y? If I'm thinking y is a constant, just differentiate as usual with respect to x. What do I get? Right, so it's a constant times x cubed when you take the derivative. You just get the constant times 3x squared. So we get 3x squared natural log y. Because natural log y we're treating as a constant here. And then for the partial with respect to y, now we're treating x as a constant. So x cubed we're thinking of as a constant. What happens? What do we get when we take the partial with respect to y? Right, so natural x cubed hangs around because it's just a constant. Natural log y, when we take the derivative, we get 1 over y. So we get x cubed over y. So x cubed times 1 over y, or x cubed over y. Right. It's really easy. You'll get a ton of practice with this. And it's really nothing new so far. Okay, so just a bit of notation, like the partial with respect to x, you might see as fancy df, fancy dx. Or you might see it as, so suppose we have, so f of xy, and we want to take the partial of it. We could write ddx of f of xy. Or sometimes we're going to write z equals f of xy. Sort of the same thing as like y equals f of x. It'll pop up in some context. So if we say z is equal to f of xy, we can also write, instead of df dx, we can call it dz dx, etc. It's just a bit of notation. And then you can do the same for y. F sub y is df dy, ddy f of xy, dz dy if it's z is f of xy, etc. Okay. So for something a bit more complicated, let's look at, how about what is the partial with respect to y? Let's look at a sort of a chain rule example of natural log, whoops, xy minus 2y squared. Suppose we want to take the partial with respect to y of this function. So we're going to need to use the chain rule here, but we're going to do the same thing we said before. We're taking the partial with respect to y, so we're treating x as a constant. Now it's just a function of y, and then we're going to differentiate as usual with respect to y. Okay. So it's a chain rule, right? It's the natural log of some stuff inside, right? So if we have the derivative of a function, an outer function of an inner function, right? We differentiate the outer function of the inner function and then multiply by the derivative of the inside. So when we do the derivative of natural log of something, we get 1 over that something, right? So we get 1 over the inside. 1 over xy minus 2y squared. And then times the partial of the inside with respect to y. So if we look at the inside, we treat x as a constant, differentiate with respect to y. What happens to xy minus 2y squared? So xy, when we take the partial with respect to y, what do we get? Treat x as a constant, differentiate with respect to y. Xy becomes, right, xy becomes x. And minus 2y squared becomes minus 4y. So we get x minus 4y times 1 over that. So we get over xy minus 2y squared. Right, derivative of the outside function times derivative of the inside. The outside being natural log, so that gives us 1 over whatever's inside, times the derivative of the inside with respect to y. Everyone comfy with that example? Awesome. So all of this is going to become really easy with just a little bit of practice. So we can also take partial derivatives for functions of more than 2 variables, 3 or more variables. Using the same rule. Except this time, so say we have x, y, and z, 3 variables. If we take the partial with respect to y, now we're treating everything but y as a constant. So x and z are constants, and we're differentiating with respect to y. So for example, if f, suppose we have a function of 4 variables, x, y, z, and w. So if this function is e to the xz plus w, nope, sorry, xz plus y over z squared plus w. Let's calculate the partial with respect to z at the point 0, 0, 1, 1. So now we're going to calculate a partial, and then we're going to evaluate it at a given point. Oh, let me just, instead of writing all that in. So before we plug in a point, we need to take all our partials. So the partial with respect to z. Okay, so we're actually going to have to do a quotient rule here because there's stuff involving z on top and on bottom. So remember, the quotient rule is low d high minus high d low over the square of what's below, if you remember the whole rhyme. It's just the bottom times the derivative of the top minus the top times the derivative of the bottom divided by the bottom squared. Okay, so we get low d high, so the bottom, z squared plus w, times the derivative of e to the xz plus y with respect to z. Okay, so now we're treating everything but z as a constant and differentiating with respect to z. Is that w in the, oh, no, sorry. That is that, ooh, what the heck was that? That was interesting. It is not. It is just z squared plus w, not z to the power 2 plus w. Sorry. That would be terrible. Okay. Okay. So e to the z plus y. We're treating x, y, and w, everything but z, as a constant. And we have e to the power, we're going to have to do a chain rule here. So e to a power, when you take the derivative, you get e to the same power. E to the xc plus w. And then we multiply that by the derivative of xz plus w with respect to z. What's the derivative of xz plus w with respect to z? Treating everything but z as a constant. Just x, right? So we get z squared plus w, the bottom, times the derivative of the top, which is x times e to the xc plus w. Oh, thank you, sorry. Times y. Yep. Sorry, e to the xc plus y, my bad, but results the same, yeah. So the minus high d low, e is e to the xc plus y is the top. And what's the derivative of z squared plus w with respect to z? Treating everything but z as a constant, differentiating with respect to z. We get 2z plus 0, or just 2z. Divided by the square of the bottom, z squared plus w, quantity squared. And now we're going to plug in the point 0, 0, 1, 1. So this means x is 0, y is 0, z is 1, w is 1 into our derivative. So we get 1 squared plus 1. So that's z squared plus w times 0. Because it's x to the e to the xc plus y. X is 0, so that's all 0. The minus e to the xz plus y. So e to the 0 plus 0. Times 2 times z, which is 2. 2 times 1. Divided by z squared plus w. So 1 squared plus 1 squared. So we get 0 minus 2 over 2 squared. So we get negative 1/2. Okay. So we can also, so those are first order partial derivatives. But so just like for functions of one variable, we can take the derivative, we can take the second derivative, we can take the third derivative. We can do the same thing for functions of several variables, except now we're taking multiple partial derivatives. So when I say partial, I just mean a partial derivative because I'm lazy and I don't feel like writing out partial derivative. Or saying it. Okay, so for function of one variable, we can take the derivative. We can take the derivative again, that gives us a second derivative. We can take the derivative again, that gives us a third derivative. There's only one kind of derivative, so there's just derivative, second, third, fourth derivative, etc. But for partial derivatives, at each step, we could take a different derivative, right? So for instance, for functions of two variables, we could take the derivative with respect to x. Let me write it like this. Whoops, sorry, no, not yet. So if we have a function f of xy, we could take the partial with respect to x of f of xy, and that gives us f sub x. Or we could take the partial with respect to y, and that gives us f sub y. So now if we take the partial with respect to x first, and then we take the partial with respect to x again, then that gives us f sub x x. So that's one second order partial. Or we can take the partial with respect to x and then take the partial with respect to y. So that gives us f sub x y. Right? First we take the partial with respect to x, then the partial with respect to y. Similarly, if we first take the partial with respect to y, and then the partial with respect to x, that gives us f sub y x. So first y, then x. Or we can take the partial with respect to y, and then the partial with respect to y again. So that's f sub y, and so on and so forth. So we can go one more level, and then we'll get 8 different partial derivatives. One more level, you get 16, etc. So now there are actually, so there are 2 first order derivatives for functions of 2 variables. There are 4 second order derivatives, and at each step you're multiplying by 2, right? But now instead of there just being 1 second derivative, there are 4 of them. F sub xx, f sub xy, f sub yx, f sub yy. And they just correspond to the different ways you can take 2 derivatives of a function. So for example, suppose our function was x cubed plus y squared e to the x. Let's calculate the second order partials of this. Okay, so really quickly, the partial with respect to x. So we treat y as a constant, differentiate with respect to x. X cubed becomes 3x squared. Y squared e to the x becomes y squared e to the x. Y squared we're treating as a constant. And then if we take the partial of that with respect to x, so we treat y as a constant, differentiate again with respect to x. So 3x squared becomes 6x, and y squared e to the x becomes y squared e to the x. So if we take the partial of f sub x with respect to y, we get f sub xy. So 3x squared, or treating x as a constant, differentiating with respect to y. So 3x squared becomes 0. Y squared e to the x becomes 2y e to the x. So then let's calculate the others. So we can first take the partial with respect to x and then take x or y, or we can first take the partial with respect to y and then take x or y. So f sub y, treating x as a constant, differentiating with respect to y. X cubed becomes 0. Y squared e to the x becomes 2y e to the x. Differentiating with respect to x. So f sub y, then differentiate with respect to x, we get f sub yx. And we get, so treating y as a constant, 2y e to the x becomes, again, 2y e to the x. And f sub y, so take the partial with respect to y, which we did, then take the partial of that with respect to y. So 2y e to the x becomes 2e to the x. So these are all the second order partials of this function. Notice in this case, f sub xy and f sub yx happen to be the same thing. They're both 2y e to the x. So at least in this case, if we took the derivative with respect to x and then with respect to y, we get the same thing as if we take the derivative with respect to y and then with respect to x. So the order you differentiate doesn't matter in this case. And in fact, that's not an accident. So this is a big important theorem. So important, we named it after a dude, Clairaut. So this is Clairaut's theorem for mixed order partial derivatives. So if you have a function of x and y, so this is a bit of technical stuff that you can forget, at least in this class. So if f sub xy and f sub yx, so both of these things are continuous, on some open disk D. Don't worry too much about what an open disk is. Here's the kicker. Then we have the mixed partials are the same, right? F sub xy at a point is the same as f sub yx at a point. And this is more technical stuff for all points in that disk. But this is the kicker. Basically, this is going to be true. The technical stuff is going to be true for pretty much everything in this class. So f sub xy is always equal to f sub yx. So it doesn't matter what order you take the partials. You're going to get the same thing. And in fact, we can extend that to higher partial derivatives. So what this means is the order you take partials doesn't matter. Even if you're taking even higher order derivatives, right? We can take a third order derivative. So you take a partial, then a partial, then a partial. Even then, it doesn't matter what order you take it in. So for example, if you have a function of x and y, if you do f sub x, then f sub the partial with respect to y, then the partial with respect to y, that's the same as partial with respect to y, then x, then y, or the partial with respect to y, then x. Doesn't matter what order you take the partials. All that matters is that you take the same number of each partial, right? One partial with respect to x, two with respect to y. You can do them in any order you like. Okay, so how do we estimate partial derivatives? So sometimes we don't know everything about a function. So we might have like a contour map or something, and we only know the value of the function at certain points, right? We have, remember the level curves. We have a few level curves of the function. And from that, we can estimate the partial derivative of our function at different points in the following way. So the partial of f with respect to x, we said the definition was the limit as h goes to 0. So we change x by a bit, a to a plus h. And we divide by, we leave y fixed, and we look at the, and we divide by how much we changed x by. So if you're going to take away the limit here, we do f of a plus a bit, let's say delta x. Sorry, whoops, shoot. Let me give myself more room here. So this is approximately, we change the x coordinate by delta x. Come on, man. Look at how f changes, and then divide by the change in x. So we're just looking at the change in our function when we change x by a little bit, divided by the change in x. At the point AB. So that's approximately the partial with respect to x. And then similarly, the partial with respect to y is we change y by delta y, and look at how our function changes. And then we divide by the change in y. So the partial with respect to y is approximately how does f change when we change the y coordinate by a little bit, delta y, divided by how much did we change the y coordinate by? So for example, let me draw a contour map of some function. So remember, contour map is you draw a few level curves of your function. Remember, a level curve is the set of all points where the function is equal to a given value. So suppose this is, oh, hang on. These are some level curves. So this is level curve, all of our function, all the points where our function is equal to 1, all the points where our function is equal to 2, 3, 4. And suppose we want to know the partial with respect to x at the point 1, 2, if we want to approximate it. Okay. So the only information we have are the value of points on a few level curves. So basically, the partial with respect to x, we know we're going to change x by a little bit. So we're going to fix y at 2. We're going to change x by a little bit. So basically, we're going to go in the x direction, in the positive or negative, it doesn't matter. But we're going to go in the positive x direction until we hit the next level curve, but just fixing y. So we're going to go over here, until we hit the next level curve. And we're going to look at how f changes. And then we're going to divide by how x changed there. Okay. So when we go along our level curve, let's say this is, so we were at the point 1, 2. We went over to, this is about like 1 3/4, so 1.75, let's say. And y is still 2. So we look at how our function changed, and then we divide by the change in x. What's the change in x between our 2 points? We went from 1 to 1.75. So what's our change in x? So it's not 0.75x, it's just 0.75, right? We went from 1 to 1.75. So it's 1.75 minus 1, so it's positive 0.75. So what is the value of our function at 1.75 at this point here? What's the value of our function? It's 4, right? It lies on the level curve 4. So that means all points on that curve, the value of the function is 4. So it's 4 where we ended up minus where we started. We started on the level curve 3. So that's 4 minus 3 over 3/4, or 0.75. So that's 1 minus 4 over 3. So that's 1 over 3/4 is 4/3. That's the approximate rate of change of f with respect to x at the point 1, 2. So if you want to know, approximate the partial with respect to x, we look at our points, we go in the positive x direction until we hit the next level curve. Look at how your function's changed, and then divide by the change in x.
How did we get the 4 and the 3 again? 4 minus 3, just to go over
So
those.
these are the level curves. This is the level curve right here, where our second point is on. That's the level curve f of xy equals 4. So that's a set of all points where the value of our function is 4. So this point lies on that level curve. So the value of the function there is 4. And so that's this guy. And then minus f of 1, 2, where we started. Well, that lies on the level curve f of xy equals 3. So the only information we have about the function is these few level curves. So we only know the value of the function on those level curves. So we have to use those to estimate the rate of change.
Wait, but it says like 1.75 comma 2 and 1 comma 2. Wouldn't that be like more towards, oh wait, 1 comma 2 would be curve 3, right? And then, well, oh,
Right,
okay,
so this is the point 1, 2 right here.
I see what you're saying. Okay.
Yeah, this is 1, 2. And this guy is 1.75. Yeah.
Yep, sorry about that. I didn't see your 2 and the 1 right there. Perfect.
Oh, yeah, it is, I guess, a little hard to see. Yeah. Okay. I think that is it. Yeah. Any questions about anything today? All right. Well, that's it for today. Have a wonderful weekend. Also, let me mention, so you will notice I did not assign any learning curves. I think I'm done assigning the learning curves. Seems like a bit too much, and I don't think people are getting that much more out of it. So from now on, the homework assignments are going to be the only things from Achieve I assign. And those are going to be due a week after we're done talking about a topic. So yeah. So with that, have a great weekend, and I will see y'all on Monday. Later.
Is there any update on grades, like when we might see those?
Okay. I guess the settings are, I actually graded yesterday, but I think I haven't made the grades visible.
okay.
So I'm going to go ahead and do that. I think the setting was to
Okay.
hide the grade until I say otherwise. So I guess I need to go in and I need to manually post the grades, but I've graded.
All right, cool.
everything.
Cool. Thank you.